Clearly. All right. Okay. So, good afternoon. We'll be presenting our progress report on the wireless power transfer system.
Okay.
This is our overview. We're going to be presenting the abstract project progress, updating the project status, individual contributions, as well as video feedback and the logbooks that we have created. So for the abstract, based on this, the advancements of wearable technology requires highly efficient wireless power transfer systems that can seamlessly integrate flexible, conformable devices. To address this, we designed and simulated wireless power transfer systems using ANSYS software, exploring configurations from Rogers to Rogers, Rogers to conductive thread, and conductive thread to conductive thread. These designs were implemented for the Brother Innovis VMS 5100 embroidery machine to produce a threaded receiver for integration. As of September 24th, the initial testing demonstrated 95% efficiency in Rogers to Rogers power transfer using a Network ANSYS machine. Oh, Network analysis machine, my fault. And 85% in Rogers to Fabric applications. These results highlight the significant progress towards developing flexible, efficient wireless power transfer systems suitable for next generation wearable devices. Juan?
And so for our progress, we have all our simulations on ANSYS. We have our Rogers to Rogers, our Fabric to Fabric, and then our Rogers to Fabric. So we've finished fabricating our Rogers 5880. We have everything soldered on, and we are also finalizing our fabric receiver on the Brothers embroidery machine, and we're going to begin soldering the textile for the upcoming test. And some of the softwares we've been using are ANSYS, AutoCAD, Inkscape, and we've also been making sure that everything is compatible with the embroidery machine. Let's finish it. Next.
Sorry. Our functionality performance currently, as we like I said before, our efficiency is currently 95% with the Rogers transmitter efficiency prototype. And right now, our critical components that we needed to retrieve was the Rogers 588 conductive thread. And right now, our technical challenges are the software integration, fabrication issues when it comes to the textile receiver. And, we are needing to achieve an optimal thread configuration when using the Brother Innovis.
Okay, so this is our NAT chart here. This is our previous one from last semester, and then we have an updated one that we made this semester. Next slide. There we go. This is our updated chart. This includes all of our timelines with things that we have completed and things that are still in the works so far. So next slide, please. And this is our block diagram. Our previous block diagram was used from the resources we were provided from previous studies. And then in the bottom is our updated simplified block diagram. As we can see, it's a straightforward line from our waveform generator to our Rogers transmitting antenna. This sends power to our receiving antenna, which is going to be made of the conductive thread textile material. Then the signal will be put through a rectifier to convert the power from AC to DC. And then this will be powering our sensors, such as heartbeat sensors, atmospheric sensors, things like this.
So our project cost currently, we stand around $178. With the changes of our products being used, we're not going to exceed the budget of 300. Our initial budget was around 3,000, but with the materials provided and the changes in supplies, then we were able to change that. And then we're moving on to our individual contributions. And this is Giovanni.
Okay, I'm working on the programming of the embedded systems, which is I researched the embedded system we're going to use, which we're going to go with Arduino Nano 33 BLE sensor revision 2. This is due to its low energy and all the sensors that are already embedded into the system. I'll be programming it with C++. I have already programmed multiple sensors, gesture, accelerometer, light proximity, and temperature to it. Next slide, please. And this is the rectifier. I ran a simulation on Multisim to verify which type of rectifier we're going to use. We decided to go with a full bridge rectifier. I built a prototype on a breadboard. We went to the lab, used an oscilloscope to test it out to verify the 5 volts DC. After reviewing the results, you go to the next slide. The results we decided to add to the rectifier a higher capacitor to be able to deal with the higher frequency, which this will be one of the challenges I'll be working on this week. And for my next step after that will be to solder it to a PCB board, integrate a heart monitor, and then hopefully build the GUI for it to communicate with the Arduino on a cell phone. Next slide.
All right, so I've been working on the design and the simulation on ANSYS electronic desktop for the HFSS. I've been creating the design to the specifications. We've been using 1.5 millimeter Rogers, and we have 3 simulation files. We have the Rogers to Rogers, Fabric to Fabric, and then Rogers to Fabric. And we added a parametric sweep for the frequency and for the distance, so 2 millimeters to 50 millimeters, just to see how that changes the S parameters. And for the Rogers to Fabric, we got around a 93% efficiency at 5 millimeters, which is good because since our application is going to be wearable, it should be around that distance. And the 5 to 10 millimeters proved to be the best, which is good since it's a wearable. And I've also been working on the CAD files for the laser fabrication. Next.
Oh, hello. And so my contribution was I was overseeing to the manufacturing parts of the process. So I was in charge of ordering and getting the Rogers, the physical Rogers. I was also in charge of overseeing the manufacturing process with the laser, make sure like everything goes smoothly. And also the initial testing. So we tested it, I believe it was on Tuesday. And as you can see here with the pictures, we got an efficiency around 92% variable depending. And this is very good because this matches up with Juan's simulation, as he said earlier. And for me, currently, my next step is I'm working to design a 3D printable stand. So because as you can see in the picture, we're holding it by hand, and this may cause interference with the frequency. So if we put the receiver and transmitter on a stand, it could lead to easier testing.
So my primary contribution lies in develop a conductive testing pattern in AutoCAD, ensuring that the design matches the dimensions of the wireless transmitter, and that this design is also compatible with the broader Innovis VM5100 embroidery machine. In order to attain this, in order to attain this compatibility, I have to make sure that the file is formatted to work with file extensions as PES or DST, which are the extensions that this machine recognizes. I also have to adjust the stitch count and density for machine efficiency and durability. Next. These are the steps that we follow to convert the AutoCAD design to PES format. After the design is done in AutoCAD, we export it with the DXF extension, and then we import it into the FreeCAD software, which is going to convert this file into an SVG extension. And follow this step, we imported the file into the Inkscape, which is going to finally convert the file into the PES extension, which is the one that we need to connect with the machine, with embroidery machine. Once we are in this software, the Inkscape, we are able to make some adjustments in the stitch type and density with the extension of this software named InkStitch. Next. And one of the challenges that we are having with this part of the project is that after follow of this step, usually the file comes with high stitch count, causing issues with the machine to recognize the file. The solution that we are going to implement is reduce the stitch density and adjust the design layout in the AutoCAD. And for my final step, we are going to proceed to testing and evaluate the conductive fabric and report final findings to the project team. Next.
Okay. All right, so I was in charge of the fabrication of the textile receiver. As you can see, we do have a prototype already made. I had to conduct multiple trials when creating the receiver ring because using the Brother embroidery machine is something new to me. So I've been working on that, focusing on what configurations needed to be used. In this case, with the copper adhesive and the conductive thread, we needed to change the configurations in the machine, such as Robertson Anton, and then the speed to 350, tension 4, and then embroidery height to 1.5 millimeters. The improvements I added, I was going to just do the conductive thread on the receiver, but I decided to add the copper adhesive in between to see what potentials may lie when it comes to creating that. So future plans at the moment, we're going to create additional receivers and explore the use of silver conductive thread. That is something that I want to look into only because I do see that silver does have a higher conductive efficiency when it comes to metals. What we're using now is a stainless steel conductive thread, but we'll continue looking into it and see what other materials are out there for better efficiency on the textile thread. Currently, a video feedback by Professor Arellano is just to reduce the amount of time of animation in the video and create more office-like environment for the video as well. And then this is our logbooks that we do have at the moment. It dates back to the month of August. Mine, Juan's, Lydia's, Giovanni's, and Javier's. I can share this document with you guys. It is an Excel sheet, so just let me know. And yeah, that is the end of the presentation. Any questions or concerns?
So if I can ask, so you said you're using a stainless steel thread.
Correct.
Why aren't you using, I think we do have somewhere in the lab our thread that's the silver thread, and that's the best one. Is there any reason why you didn't use that? I guess you're learning or?
Well, I wasn't aware that you guys actually had silver thread.
We'll have to look if we have it.
Mhm.
Also, do we have it?
I'm not sure. I have to check. I didn't know that we had, so
Yeah.
I haven't seen any around. I think the last one was used for the quadrifilar helical antenna.
So we used it all?
The last guy that we got, after that it was another one, but maybe DF took it.
Yeah, so we gotta look in the drawers to see if we have
Yeah, I checked the drawers, there's nothing there, but I don't know if there's
Nothing.
any.
So you don't think we have it?
No, I doubt.
Okay.
Okay, so I guess we'll look into that, so we can better improve the receiver, on our end. But I think, yeah,
The
that's
other,
pretty much it.
the other thing. So what are you envisioning you're gonna have as a demo at the end of your, like, for your senior design? Is it gonna be a vest where you're gonna put that? Is it gonna be just like on top of the desk, or how are you gonna set that up so you can demonstrate what you're trying to do?
Gotcha. So I do have a rendering of like a stand of what we want for testing, but my envision was to actually sew the textile receiver onto a shirt
Yeah.
and then have that same vision that you guys had on your previous reports with the vest that's in your lab and try to simulate that so we can have that as a display for our senior design project. So that's what my envision is for this project, is to have like a shirt and the vest. So as per se, like showing that demonstration of wearing a shirt with the receiver and the heart monitor that we have, or the multiple sensors that we're planning on integrating, and then the power, which is going to be the vest, which is going to be the transmitter onto the receiver like this. So pretty much like that. So that's my envision. Now, worst case, we'll have that stand that we would like to demonstrate as well. But at the moment, the way I'm envisioning our timeline, we'll probably be able to make that vest and put together as demonstration. That's the end goal for us.
Okay, good.
Mhm.
That's good. So the other question I have is, you chose this Nano, I guess, Arduino. What it is, an Arduino, right? Nano.
Yeah.
And do we know how much power this takes? Because the problem a lot of times with the WPT is how you're going to deliver enough power, and especially the current you need there to get that to turn on. Do we know how much power that needs?
Yes, it needs a 3.3 volts
Mhm.
DC. It could
Mhm.
handle up to 21 volts DC, and so it could fluctuate. And that's powering all the embedded sensors inside of it with that come with the set the Arduino. That's
Mhm.
also including the BLE, sorry, Bluetooth Low Energy, to be able to send signals. Now with the heart monitor sensor, well, I'm looking into it to see which one we could find that will consume the least amount of voltage, so we could power it with the system.
Because that's one thing, you have to know how much power you need, because then you gotta backtrack. So if you're gonna lose, let's say, if you're gonna, most of the power is not gonna be lost in the WPT link, at least if you're doing it not on the human. Let's assume there's nothing there, just for starters. So let's say you have 90%, like you're showing efficiency, but then when you put the rectifier, your efficiency is gonna go down to 40% of that. So then you have to backtrack the other way. So if you have to deliver a certain power, you know your overall efficiency for the whole system after rectifying. So then you have to see how much power you need to transmit. And if that power is too big, then something is got to be changed in the design. Right? And then the other thing I wanted to ask is, when we were designing our latest stuff, we had found these, and I'm forgetting now what was that chip called, or that little circuit component we would buy. It was already a package, and it had its legs and everything. So it was already giving us the bridge. And it actually even had I forget what that circuit called. It's called something. It's essentially doing what you did with your capacitor. It smooths out so you can get DC. Otherwise, if you just go with a regular rectifier, your output signal is going to be like a mess. So, and I think that chip that we had included all that. So I wanted to bring that to your attention. Are you aware that maybe you can use something, and maybe that way you can get better performance or you're planning to use your own rectifier and design your own rectifier?
So for that, our initial plan was to design our own rectifier, and right after the rectifier, put a low pass filter to try to filter out as much of the interference signal as possible.
Yeah.
That was
it
our
might-
initial plan. Yes,
Yeah, it might be
we
worth though to look at that part. If I can try to find it, I'll work with Tassos to see if we can find that part, what it is, because I don't think it's expensive. It's like this little part you can buy, and then that may give you better performance. So and you can compare it to yours and see what you get.
Sounds good. So yeah, we should coordinate with each other for the part as well as for the silver thread, so we can improve on the project. So I think, yeah, that's a good idea.
And then the other thing, like I was telling you when we talked a few weeks ago,
Mhm.
is that that's why I was asking about the demo. If somebody's going to wear that thing, then when you wear it, that might also change your performance.
Yeah.
So the WPT may be completely detuning. But if
Mhm.
you're planning to just have it like on a phantom, like you know, we have in the lab,
Mhm.
probably that's good enough for demo.
Yeah.
I wanted you to
Yes.
be aware that maybe once you put it on top of the body, it may be
Mhm.
some detuning there, and the efficiency may drop.
Yeah. Yeah, no, we were gonna use the model that you guys have, the humanoid
Mhm.
figure, because
Yeah.
I think it's better to have that demonstrated, because as well as we don't want nobody getting hurt or affected if something goes wrong with the circuits or anything like that.
Yeah, that's
So I
fine.
think having like just a model with the shirt and the jacket or vest is
Mhm.
the best way of doing so. So there's no injuries or anything, and like there could be better efficiency with that.
That's fine.
Mhm. So yeah.
And the other thing, I saw an element, I couldn't understand the one you showed where you had the copper, but I think
Oh,
that element is shorted the way I see it, but maybe I don't
this one?
understand. Yeah, that's just like done. That won't work. You shorted the magnetic flux, so I
Mhm.
don't think that's gonna work at all.
Well, by that you mean the reason the copper is laying out completely flat like that?
You
Or
can't put the element on top of a metal. It won't
no?
work. You can test it and see, but I don't think it's gonna work. I mean, sure, there's no way for the magnetic flux to go through
Mhm.
and get you know, create the coupling that we want to create through the wireless link.
Gotcha.
So you want to leave that, you know, without. In fact, we did research on that because that is a problem when you bring these WPT elements near grounds.
Mhm.
And I think we might have didn't we publish one thing, Konstantin?
Yes, here this will short because you have the copper between the inner and the outer loop. You see there how there's a
Yeah,
piece of
that's what I'm
copper.
saying. Yeah,
If you remove this, then it will work, but
yeah,
you will not be able to stand.
Yeah.
You can use a different substrate underneath, and
Mhm.
that's I like that you have copper on top of whatever it is because you can increase the efficiency.
Mhm.
It's still flexible, so it will not break. But you need to put something underneath, put denim as a
Mhm.
support, as a substrate, and remove all this copper between the loops, all the areas. And in the inner loop, you shouldn't have
So
any. The copper should only be behind your rim,
give me one
if it
second.
makes sense.
Yeah.
So yeah, just leave the copper there and the rest.
But I think if they have copper really close to the elements, I think they're gonna be detuned. I have a feeling it's gonna go down to. Have you tested that element?
So we haven't tested it just
Yeah, I
yet,
think you're gonna get
but
0 out of that. But
as you see in the
even if you clear the between, I think
Mhm.
still you're gonna get very low because we had always a problem. These things, the moment you bring them close to ground, because we even I think published one work where we were putting, if you want to help that situation, you basically put a ferrite material, and the
Mhm.
ferrite isolates ground plane or the metal under the receiver.
Mhm.
But if you just put it like that, very close, basically you short the coupling, and
Yeah.
and then your efficiency will go down to like 0.
Okay.
But if you like the one on the right, you see how it's like one, let's say it's essentially one side with a
Mhm.
single loop, and then the other side is the other side. There's gonna be like a piece of denim in the middle of that, and
Mhm.
all the copper, that the excess copper is gonna get taken out.
Yeah, we don't want copper. Yeah.
Okay.
Yeah, so on the top right corner, basically, those two are actually separate. They're not like one receiver in total. It's actually separately. So like Juan said, we're planning on putting like a DEMNUM in between because we realized with the Rogers transmitter, they're separate. So we want to, add that context into here to see what would happen because all the examples that I've seen in the lab, they're all hooked together. So we want to see how that changes with our version of the design goes. But yeah, we'll look into that and we'll test what would happen with the copper in between. But like you said, it may short, so we'll
Yeah,
see how.
you don't want any copper, basically.
No.
The copper, you can have copper,
Mhm.
but copper only basically mirroring the shape of the two loops. That's okay,
Gotcha.
but nowhere else.
Exactly.
I think if you
Okay.
have it anywhere else, it's gonna be gone. Your coupling is gonna go to 0.
No, of course. Okay.
Yeah.
Sounds good.
Yeah.
We'll do those changes then. All right. Any other questions, concerns?
No, I think your major thing is to figure out the power of the Arduino and can you
Okay.
turn it on?
Yeah.
And you can do, because you have a team, right? So you can be working parallel. So you don't need the people that are dealing maybe with the elements design. They don't have to deal with that. The
Mhm.
people they're doing with the Arduino and the circuit part, you can just go and try to see how much power this thing, what's the minimum power to turn it on. And then from that, you can just do a simple back calculation. If you assume like 40%, let's say, efficiency in your rectification, and then 90% efficiency for the wireless link, then you figure out how much power you need to send. And then once you tell us that number, we can figure out, is this easy to do? Is it difficult to do?
Mhm. Yeah.
So
I also saw a different part that's not Arduino. I think it's called Adafruit. They also have like a part that can be with
we've
conductive
used that
thread.
stuff before, the
Oh
Adafruit
yeah?
and all that stuff. We've used that because we were picking the lowest power possible.
Yeah. From what I've seen, the Adafruit one has the lowest one. So we'll see how we would switch gears with the Arduino to the Adafruit.
And it's good to keep us posted, so keep us, updated. So once you find that, you can tell us quickly, so you don't go down a path and do everything with, let's say, the Arduino, and then we figure out in a month from now, we're like, we can't generate this power. It's
Yeah.
impossible. So it's better to figure that out quickly because it's going to be a critical part of the design for
Yeah.
it to work.
Okay. Then we'll keep you guys updated weekly. Every Friday, we'll send out emails letting you guys know how our progress is. I did send the timeline, but we're gonna update that soon. But yeah, we'll keep you guys updated for sure.
Okay.
All right. Well, thank you guys for joining, and yeah, have a great day.
All right. Okay, we'll talk to you soon.
Yes.
Thank you.
Okay, bye-bye.
guys.
Bye.
Yeah.
Bye, everybody.
Bye.
Bye-bye.
Bye.
Hello.